7-6 probability distribution. If you remember that table on page 427, we're going to be dealing with that particular random variable. What is a random variable? It's the variable that we're studying. When we say random, it's because we don't know what's going to happen with it. For instance, a probability distribution a lot of times will be set up in a chart that looks like this. We have our list of outcomes, and since our random variable that we're studying, like on page 427 shows you the red dice, white dice picture, but what we're talking about are X represents the sums of the dice. So, yes, the lowest sum we could possibly have is 2, all the way up through 12. Now, the probabilities come in that we need to count how many fit into each category. So, we might have to look at a sample space and say, okay, when you look at all 36 different options, how many of them are 2s? Well, I only see one of them that's a 2. So back on my chart, I would have 1 out of 36. And if I go through this chart and I count, well, I'll have 2 of these, and 3 of these, and 4 of these, and 5 of these, and 6 of these. All of a sudden I start getting back to ones where it starts going back down. Then 5, 4, 3, 2, and 1. So I can fill out my probability distribution chart. 2 of these out of 36, and 3 of these out of 36, and 4 of these out of 36, and 5 of these out of 36, and 6 of these out of 36. Back to 5, 4, 3, 2, 1. Now, obviously some of those can be reduced, but I'm just looking for a quick way to write the different probabilities. Now, are we going to use our calculator for some of this? Well, certainly we are. So in order to use our calculator, we're going to hit the stat, enter, go into our lists, and we're going to type in the values or the outcomes in list 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So those are the outcomes. In list 2, I want you to watch how I'm going to enter these. I could hit 1 divided by 36, and 2 divided by 36, and 3 divided by 36, but I'm going to put just the numerators. Now, you're probably wondering why I'm doing that. Well, in order to save a little bit of time, I've entered the numerators, but now I'm going to go back up to the top of the list, which is list 2. At the very top, I'm going to hit list 2. You can find that on the number 2. It's one of the second features of the number 2. Divided by 36. So in other words, I'm going to take all the values in list 2 divided by 36 and stick them back in list 2. By doing that, I've changed them all to probabilities or percentages. Now, what do you think if I go to second stat math? What do you think the sum of list 2 will add up to be? If you add up all the possible probabilities, shouldn't you get the whole number 1 for 100%? That is exactly true. A true probability distribution adds up to 100%. So, they have a couple questions in the homework where they ask you to prove that something is a good probability distribution. All the probabilities have to be between 0 and 1. Clearly they are. And the sum of those adds up to 100%, or the integer value 1. So that's how we can use our calculator to get some data into our calculator. Um, an experiment is not from a sample space. An experiment is when we roll the dice a certain number of times. So for instance, let's say we're doing what's called a relative frequency distribution. Relative frequency distribution. Whoa. Now, in this relative frequency distribution, because it's from an experiment, it's not going to be out of 36. It's out of the total number of times that we tried whatever the event was. So in this particular situation, you can see that we rolled the dice 78 times. And when you roll the dice 78 times, you are dealing with relative frequency, not probability. So you see, I notice I have R of X instead of P of X. Now the outcomes are still the same, but when we rolled the dice 78 times, 2 times we got the sum of 2. 4 times we got the sum of 3, 6, 6, 13, 12, 14, 11, so on. You are going to notice that it is not perfect like the other one. In fact, if we came back up and we took a look at the graph of the first one, so let's suppose I made a graph. Let's see if my graph's already set up for it. No, it is not, so let's change the window. 0 to 14, that's good, right? Sum of 0 all the way up to a sum of 14. The maximum, that looks about right. I think I did change this earlier, but the maximum probably, let's go 7 divided by 36, and go by increments of 1 divided by 36. Okay, and let's see what our stat plot. Let's set up a stat plot. So second stat y equals, and then that's your stat plot. Turn one on. Make sure it's a scatter plot using list 1 and list 2. Now let's go to the graph. Notice how perfect it is. How perfect all the values are. Well, suppose I go back into my lists, and I'm going to go over to list 3 and 4. And I'm going to, actually what I need to do is just use the relative frequencies. So I'm going to type in the numerators from my relative frequency distribution, right? 2, 4, 6, 6, 13, 12, 14, 11, 5, 2, 3. I can set up a different stat plot, maybe shutting the first one off, or maybe I'll just leave it on. But this time I'm going to do list 1 and list 3. List 1 and list 3. Now, one thing I forgot to do that I'm going to jump back into those lists. The thing that I forgot to do was go up to the top and divide that whole list. So list 3 divided by 78 observations gives me the probabilities. What do you think the sum of list 3 is? Still 100%. That's not going to change. So the sum of all the probabilities, whether it's a probability distribution or a relative frequency distribution, is not going to change. All right. So what does the graph look like now that we've changed those? Oh my goodness, look at that. It's not exactly perfect. Now, does it still have some of the same type of shape up and down like that perfect shape we had a few minutes ago? Yeah, it still has some of the same type of shape, but you can clearly see that it's not perfect. Experiments are never usually perfect. Only probabilities and from sample spaces, those kind of things are nice and perfect. Well, so now you know how to make a probability distribution table, and you know how to create a graph. And if you need help with the making a window, we can talk about that too. Zoom 9 is always a good thing. Zoom 9 helps you to zoom in on your statistics. Now, something else we need to talk about. Whoa, a little too big there, sorry. The average or the mean of a probability distribution. Keep in mind, a probability distribution comes from a sample space. Relative frequency distribution comes from an experiment. Now, two different letters we're going to use for the average, depending on which situation we're in. Mu, yes, that's pronounced mu. Not like the Pokemon character. But, kind of got the same idea there. Greek letter mu. And then we have X bar. Yeah, I know, it's a very clever name for it, X bar. Both of these letters represent the average. And I know you're getting hung up right now as you're copying down the summation symbol and the formula. But I want you to understand and look at what we're doing. You're adding up a bunch of stuff, right? Starting from the first observation and going all the way to the last one. And we have all the outcomes. So X sub I represents the outcomes. And P of X sub I represents the probabilities. Once again, over here I have outcomes. Whoops. And relative frequency. Well, that's the probability based upon the experiment. Both are calculated the exact same way. Don't panic about this. It's not about the notation. Look at this. This makes it a lot easier. You've got all of the outcomes in list 1. And either you have the probabilities, because it's a probability distribution, or you have the relative frequencies, because it's an experiment. You have those in list 2. The expected value, or called the mean, is found by taking the sum, oh yeah, that's what we're using for that sigma notation, of list 1 times list 2. Now, I'm going to do that for what we were doing before. So sum, list 1, list 2. Now this is the expected value for the probability distribution, for the perfect graph. 7. We expect, on the average, to roll a sum of 7. Now we use the Greek letter mu because we're talking about the probability distribution. Okay? I say the average over the long term because we know that each time we roll, we're not going to get a 7. But on the average, if you were to average a bunch of different trials, you would end up with an average of 7. That's the perfect situation. Now, what was the average of my experiment? Well, we used list 1 and list 3 for the experiment, right? List 3 was where we had all the relative frequencies, and it has an expected value of 7.06. In other words, in my experiment, it was not perfect. So X bar was approximately 7.06. Okay? Now, as you take more trials, so more trials means that X bar gets closer to mu. X bar gets closer to mu. That is an extremely important point. As X bar, as you increase the number of trials, X bar gets closer and closer and closer and closer to the true average. See, this is an estimate of the average based upon an experiment, and this is the true average. Estimate, truth. Okay, now, we just did this, so I don't need to do it again, right? We just calculated that mu was 7 and x bar was 7.06. So we've got that taken care of. What is the percent error between them? Percent error is found by taking x bar minus mu and dividing by mu. So 7.06 minus 7, not too difficult, divided by 7 is 0.00857 or 0.857% error. Not even 1% away from the true average. That's pretty close. Example 2 talks about the number of boys. So the random variable in this case is the number of boys out of a group of 3 kids. 3 kids are born. We're going to count the number of boys. Sorry, girls, don't mean to offend you, but we had to pick somebody. This is just who they chose in their example. We're looking at the sample space. The sample space, there are 8 different possibilities. How many of them have 0 boys? Well, there's only one of them right there. How many have 1 boy? Well, there's 3 choices there. How many have 2 boys? Also 3 choices. How many have all boys? There's 1 out of the 8 choices. Obviously, the probabilities are out of 8 because the sample space has 8 options. So, we can find the expected value of this. So, let's go to our lists. We got list 1, list 2. Get rid of the data we had before. 0, 1, 2, 3. 1, 3, 3, 8. Oh, 1. Excuse me. Divide the whole list by 8. List 2 divided by 8 changes them all into probabilities. Going to go back to my home screen. Remember, somewhere back in here I can use sum of list 1 times list 2. I know that's the way to find the expected value. It's 1.5. So, the expected value, sum list 1, list 2 equals 1.5. Did I find mu or did I find x bar? Well, of course I found mu because we're dealing with a sample space, and these are probabilities. This is not some kind of experiment. It also talks about making a histogram. Folks, if you can make a scatter plot, you can make a histogram because you can set your details for your scatter plot. You can then do zoom 9 and you can come up with the 4 different heights of the bars. If you want to do a different picture, you can change the window. Say the Y min goes from 0 on up. Maybe then look at a picture like this and draw bars to the individual heights. That's the type of picture you'd see in the book. Instead of using dots, they use bars. So we can make a histogram based on that information.